Thank you so much, Timo and Kai. Can I check that you can both hear and see what I'm talking about?
Yes,
sure.
Sure. Good.
So I'm grateful to you for inviting me. It's wonderful to be here. I'm going to talk for about 25 minutes or so, and I would appreciate, Timo, you letting me know when I've got about 5 minutes left so that I can find myself to the time. I want to talk about, let's see if I can successfully advance the slides, a range of topics here under the title there of applications and challenges on the road to the exascale. But first, I will acknowledge a range of people. They're listed on the left. It's only a component of those who've worked with me on material that I'm speaking about today. On the right-hand side, I am listing a number of funding agencies and institutions with whom we are actively collaborating here and now and fund our research. As Timo knows only too well, and others should too, he mentioned it, I personally have enjoyed substantial and continue to enjoy substantial funding from the European Union in, at the moment, Horizon 2020. I will have reason to be mentioning this repeatedly during my talk. I noticed that apparently after the 1st of January this year, we've become global Britain, and that suggests we're not interested in what's going on in Europe, and we'd be better off finding out what the Americans are doing and the Japanese and the Chinese. Well, I think it's very interesting what they're doing, but actually we are still in EU programs, and it's in our interest to remain in them. And the reason for that, if it isn't clear already, surely will be by the time I've finished, and that is because the EU is funding at a very substantial level high performance computing in its new programs, Horizon Europe, which the UK is now intending to sort of rejoin in a lesser position because we can't influence what it does anymore. But the other strand that's coming out of Horizon Europe is called Euro HPC, and anyone who wants to play the game of high performance computing at the exascale in Europe needs to be part of that. And unfortunately, because of Brexit, the UK decided not to engage in that. But I suggest that there's a possibility we might be able to consider our position there again. And I know some people in, let's say, funding agencies here and now are working to try and make that happen. And during the course of my talk, I hope you'll realize why that matters to us. That's what I'm going to talk about on this set of slides, the kind of resources I'm able to use here and now, not what I aspire to use, but also, of course, what might be coming down the road. And then there are the applications, because this is fundamentally an applications workshop, and we do work across a range of areas. So I'm only going to give what we would call a potpourri or mixture of things we work on, which emphasize some of the messages that I'm going to come out with during my talk. And that set of messages in terms of algorithms and methodologies will come on the next slide, and it maps into different applications that for systems engineering we could hope to exploit on the route and path to the exascale. So what I'm really interested in, and I run a large European Centre of Excellence in high performance computing. I mean, the European Union is actually wanting us to call them in exascale computing now. It's in its second set of a 4-year current funding period. We've just had the first year of it. It's in computational biomedicine, and there are maybe 12 of these now across a range of sectors that the EU is funding. But the emphasis is on, they're supposed to be user-driven centers of excellence, but now because of their drive to the exascale, the idea, by the way, was to make the Europe independent. We won't discuss what the political significance of that might be, but to be able to stand on its own 2 legs in terms of producing high performance computing in an industrial sector that might be making machines and running applications that use them. So these centers of excellence are actually central to the Commission's interests in being able to show that when its exascale machines arrive, there will be applications there running on them. And that's an interesting issue in its own right. But for my area, the interesting thing is that if you look at computational biomedicine, which is a nascent underdeveloped but very kind of pregnant with opportunities field, we don't have any single kind of model for the way we want to do computation. And broadly, I want to emphasize that there are three categories of computing we're interested in, and they're listed here. One of them we call monolithic, which you might regard as the conventional and perhaps traditional old-fashioned extreme scale version of supercomputing, where you have a single application and you deploy it across, you know, a very large fraction, if not the entirety of the production partition of your machine. And in the conventional route, that's what justifies building supercomputers, because of the interconnects. And so if you're trying to build an exascale machine now, you, and when I say you, I mean think of yourself as a project officer or a commission officer in the European Union, are trying to push people to show already that they've got codes that are exascale prepared. And the reason is going to become clear when I tell you what machines are looming. But of course, we're not just interested in monolithic applications, and in general, they're not the largest class of interest to many of us. We have coupled simulations. We heard about those in kind of weather and climate for sure yesterday and other areas. And that's a very common thing now, which is related to multi-scale and multi-physics scenarios where you've got different codes that are actually coupled together. So HemelB is the first instance in item 1. I'm going to tell you about that code. We have another one which is in materials in item 2, but actually HemelB is itself, even though extreme scale, also a code that we couple both to itself and to other large scale applications. And finally, there's this area we call ensemble simulation. Shantanu Jha, if you were here yesterday, spoke about that very eloquently, because this is the one that's sort of coming up on the outside, and most people, including my colleagues in the commission and project officers, seem only dimly aware of it, where you can actually develop incredibly complicated applications, which are kind of mosaics of subcomponents. But in the first level of it, it might sound incredibly boring. Ensemble simulation means I've got to run lots of replicas of one and the same thing. But those same things may be themselves extreme scale applications, and in other occasions they may be small. So it's a very diverse portfolio. We have applications in all of those areas, and we look at where they run on these machines. The point about item 3, as Shantanu Jha mentioned yesterday, is they open the door to extremely complex workflows in which we can connect conventional HPC running at pretty large scale with these modern trends in machine learning and artificial intelligence. So these are the machines we use today, and we use them in production, not just testing. And you can see they're pretty substantial, and they're all largely now heterogeneous. That means, you know, you've got accelerators and multi-core nodes on the machines. So I mentioned the ones in the first bullet point that we're active on now. They're positioned in the top 500 if you care about that. And then upcoming machines such as Archer 2, which has just become kind of a production scale machine. But what's interesting for you in Europe is these next two machines are pre-exascale machines, and they're expected to come in for Leonardo at Cinica perhaps by the end of 2021, and Lumi at CSC in Finland in 2022. And those are aiming at around half an exaflop each, and they will have those kind of accelerators on them. We need to know about those architectures now, because I'm responsible for a center of excellence, and I'm answerable to the commission to show them that we have codes that can be transferred and deployed onto those last two machines as soon as they hit the ground. So that requires this notion of code design to be taken pretty seriously, although what that means in practice is variable, from the idea that you're developing codes when a machine is still on the drawing board, which is pretty rare, frankly, to the fact that I've got advance notice now of the architecture of Leonardo and Lumi, and I can make steps to modify my codes that I'm telling you about in this talk so that they will run at that scale there. So those things will have, you know, millions, several, at least 1 million cores, I'm sure, each, and several, probably tens of thousands of GPU cards on them. Now, the thing is that if you're fortunate, as I am, to be able to be running large allocations of production jobs on Summit today, the architecture of Summit is one that maps very closely onto both these machines, Lumi and Leonardo. So the fact that I've got applications that run on Summit now will help us a lot with our European colleagues in 12 months or so. Leonardo is a machine which will have Atos, Intel, and NVIDIA GPUs on it, and Lumi will be a Cray Shasta machine with AMD GPUs on it. So that much we know, and despite the fact that I said Europe wants to be independent in terms of building HPC machines, there's one heck of a lot of US kit in both of those. Here are the applications. I've talked about those with great pleasure in a UK COMES meeting before, and I will just have to skim pretty rapidly through these things here. The code has been developed under UK COMES, the High-End Computing Consortium, and through the Comp Biomed Centre of Excellence. It's a large-scale, C++ flat MPI parallel code. It's designed to handle sparse geometries. It's not trivial to parallelize this as a bulk lattice Boltzmann code would be. You have to use indirect addressing to handle these sort of highly sparse and unstructured flow domains that we work with. But still, it's there and it works. And I'm just going to take you through some of the scaling. And the reason why we do this is, A, I have to for a living because I'm answerable to the Commission, and because we want to run now very big applications on these machines. So here are a few features of HemelB. On the right-hand side, showing SuperMUC NG, which is the machine at Leibniz Rechenzentrum. It has around 6,440 nodes on it. They're all Intel processors on the cores, about 48 per core. And we can get linear speed up onto about the entirety of that 311,000 cores. And that's what these plots are roughly showing you. There's a lot of work that's been done to get it to that position. It's become a good case, a use case for the MPI-4 standard, which, believe it or not, until now was only managing to shift around 32 bits, but now 64 is vital for the scale of data that we ship. There's also an all, which stands for a load balancing library from another center of excellence called ECAM that's being used to assist with the scalability here. And we work with other COEs like POT, the performance optimization one, to really optimize these things. The Archer 2 performance out of the box is very good, up to about 131,000 cores, because of all the effort we've gone to before. We've been able to join the ExCALIBUR Performance Workshop series recently to look at I/O and accelerator performance inside the UK scenario. One of the questions, though, is when we're in these heterogeneous environments, how do we deal with and monitor, let's say, measure the scalability of a code when it's got CPU and GPU versions? So we have developed a GPU version of HemelB, and that's representing the effort of something like 15 person months of people getting it to the position where it does run. I'll show you how it performs in a minute. But what we're asked to do for the Commission and at risk with these agencies is that they want you to show it running on hundreds of thousands of cores. But of course, if it's a GPU code, what does it mean to run it on hundreds of thousands of cores? It's the GPU count that matters. Yeah, but the GPUs are far less, let's say 1 to 100 on a machine like Summit. So getting a reasonable representation of performance for these people who are demanding evidence of scalability to the exascale isn't trivial. After all, the number count is in favor of CPUs, but the parallel threads or even cores that are referred to on GPUs, one GPU has effectively 10 to the 3 threads or cores on it. So you're in an imbalanced situation. What we do need for all of this in the end is better metrics in order to monitor performance capacity, and things like peak flops and node count are going to be more interesting than raw core or GPU counts. So we have a lot to worry about there. This is just to give you a flavor of the comparison between our GPU version of HemelB and the best multi-core version. And this is trying to put a lot of data onto one slide. If you're in the LB or lattice Boltzmann community, you know you don't even care about flops or other measures. It's MLUPs, which are millions of lattice updates per second. How many of those can you get out of your code? That's what people want to know. And the answer is shown on this slide, where the top performing code by a country mile is Summit, which has 6 times V100 cards on each node with 48 power 9 from IBM cores. So what you see here is it's not a weak scaling curve. It's actually just the same model size as you put more and more nodes on the problem. And of course, what you do see is that there's a degradation, and that degradation is a combination of the nature, the amount of computation you're doing versus the communication as the node count gets larger and larger. And these bottlenecks also impact us in a way which are related to HPC facility design that we didn't have a say in. If we were co-designing 10 years ahead, maybe they would have paid attention to us. So here's another way of looking at the performance for all of the code, all the versions of HemelB on CPU and GPUs sped up, but sort of on one and the same curve as a function of the actual machine they're running on. And you can see Archer 2 down there, which is running up to the biggest core count, and then SuperMOOC NG with its 311,000 tapering off towards the end. The tapering off, I mean, most of the performance of the codes at the moment here are able to report 75% or more of theoretical peak, let's say, linearity before the communication bottlenecks kick in. But the bottlenecks are due, as I was saying, to the geometry. The very size of the problem we want to handle becomes difficult to get onto the machine in the first instance. But we know with great confidence that if our models get larger, the scaling will persist in a linear fashion. And here's an example of a GPU versus a CPU flat comparison in terms of wall time and scalability for HemelB on SuperMOOC NG, the upper curve, and this is wall time, so the lower down you are, the faster you're moving. So SuperMOOC NG is linear to essentially the whole of the machine, close to it with the size of the model. And on Summit, so far, the largest count we've run on is about 2/3 of the entire machine, which, depending on how you define it, has 2,400,000 cores and around 25,000 GPUs. So this code is scaling on up to currently 18,000 or more GPUs, and it's doing a good job. It will continue to do it as the model size gets bigger. So the reason why I'm doing this is I'm a scientist. I might have forgotten that, and you could have done while I'm talking. We need to be able to apply this to big problems. And a kind of problem that I discussed in a UK COMIS meeting is this. We aim for aspire to do whole human scale simulations of blood flow.
5 minutes left.
Yep. And this is an example of where we take a whole human left arm in this instance and look at how we can analyze ahead of time a potential intervention that a clinician would conduct in order to carry out a dialysis in an effective way. And we can do this by simulation of patient-specific geometries that we get, and then run them through the HemelB fluid solver on machines where we might be using up to, say, 30,000 cores for these calculations. Time is short, so I won't be able to actually take you through a lot of the science here. This is a paper that's in preprint form, and you can access it from our web pages. It's currently under review, but we can see, in fact, that the behavior of the system is very much similar to the aspirations that clinicians have to clean out the area after some kidney dialysis. The details here are not going to be digestible in the period of this presentation. But down on the bottom right, we do find satisfying agreement, in inverted commas, in terms of the flow and venous diameters that we are using in our model compared with clinical data for the other points from for comparison. So obviously this is for improving interventions in the future on a large scale. We have different applications that run on different types of systems. This materials case, again, I've discussed this before, it's a different pattern. It's a coupled form of calculation, and it's cyclic, so interactive between a finite element and a molecular dynamics code. And this requires spawning of very large numbers of independent molecular dynamics simulations as required to handle localized areas of a material which might be in danger of fracturing and so on. So we can deploy applications like this onto big machines, and they will scale very effectively. This code is under development and only now sort of beginning to become optimized for very large scale deployment. We're running it on tens to hundreds of nodes on SuperMOOC NG at the moment. The back is the binding affinity calculator. I'm going to assume that people were lucky enough to hear Shantanu Jha talking about this yesterday. It's an interesting and complicated workflow in group 3, which is ensemble simulations for molecular dynamics, and then the connection of the molecular dynamics workflow to actually informatics and machine learning capabilities, where we do docking of drug candidates to proteins. We then use a combination of molecular dynamics and artificial intelligence to find some improved bindings between the ligand and the protein. And the last step of the workflow is to transfer into a high fidelity free energy calculation that's purely physics based. And all of those things are being iterated again on machines like Summit at very large scale. So that's something that the complexity of the architecture enables us to tackle a really large problem very efficiently. So I think I will just begin to wind up here, because Timo will be telling me to stop. I want to reiterate something which is to do with uncertainty quantification. Timo mentioned that. I'm running a project called VECMA at this point in time, but also in terms of ExCALIBUR, there will be people who know UKAEA is one of the 3 partners with the Met Office, and it's planning some new codes to handle fusion energy modeling and simulation for tokamaks and design purposes in the UK. And from the start there, they want to have uncertainty quantification built into the fabric of the coding. So I'm happy to tell you that I'm involved with them in working with them in that initiative, which should be relevant to what we're doing in this project and also Met Office applications. And just whet your appetite briefly by telling you about something I've spoken about. It's now actually accepted for publication as of earlier this week, which is just looking at the level of predictability or reliability of codes like Professor Neil Ferguson's, called COVIDSIM now, which was used by the UK government famously to inform whether it would have a lockdown or not. I'm going to run out of time talking through this, but if you look on the right-hand side of those graphs, you'll see this enormous distribution of outcomes that are possible from that code that he has available. When he ran the simulations, he just did a one-off case with those orange dotted lines and suggested there would be a number of deaths after a number of days, as shown here. But the code actually supports enormously larger numbers of death outcomes than was seen, than was reported at the time. And the green graph, the plots there, are actually the data that accumulated from the event itself. So you can see the importance of understanding uncertainty in your application, which can be huge. What's propagating the uncertainty? In this case, it's overwhelmingly parameter uncertainties that lead to amplifications of a factor of 300% compared with the input uncertainty. And that needs to be taken into account. So we have the wherewithal to do that, but at scale, you have to use pattern number 3 and ensemble simulations in a major way. And with that, Timo, I think I've reached the end. The summary is here. We are interested in exploiting high performance computing resources all the way to the exascale. It's coming close for us to tackle big problems where we have step jumps in what we can ask, questions about now, virtual human being one of them, and trying to measure the performance of these different compute patterns is itself something of a challenge that needs discussion. And with that, Timo, I will stop and thank you for your attention.